Okay, so continuing on 4.6, we're going to find the points of inflection and the intervals for which we're concave up and concave down. So whenever we're asked to do this, we need to make sure we get the second derivative, which is just the derivative of the derivative. So we're looking at 12x squared minus 24x. So what we can do is factor out a 12x. We're left with x minus 2. So we're looking at x equals 0 and x equals 2. And we can make a sign chart from this. Negative times negative is positive. Positive times negative is negative. Positive times positive is positive. And then from that, we can conclude that it's concave up from negative infinity to 0, union 2 to infinity. Don't worry about brackets. Typically, we have directions that are like the open intervals, so that shouldn't be too bad. And then from 0 to 2. And just a few more questions before answering this. I hope you remember back in pre-calc how we talked about, we could factor out at x cubed and then x minus 4. So these would be your roots in the original problem. Well, if you have a multiplicity of 3, it changes concavity at x equals 0 there. So without really doing any math, this graph with its end behavior is going up and to the left and up and to the right. And at x equals 0, it changes concavity there. Things that we talked about in pre-calc. Plus, you can verify with the end behavior that it's concave up first. I know I didn't draw it very well. And then concave down, and then concave up. We could find the points of inflection, like 0, 0 is for sure a point of inflection. And then plugging in 2 at x equals 2, we can figure out the other point of inflection. I'm way too far up there. It would be, I'd probably just do it this way. If 2 cubed is 8 times negative 2, so it would be negative 16. So 2 negative 16 is the other point of inflection. But one thing I forgot to do is mention y, like with your justification, because the second derivative is positive on that interval, and then this one would be because the second derivative is negative on this interval, so less than 0. So there's your justifications. As I move on to the next one, a little tricky parts to this. Not too bad though, because you could probably notice that this is going to be, whoops, before you can find the second derivative, you better find the first, which is your product rule. So the derivative of the left is just 2x, leave e to the x alone. Now leave 2x alone, but the derivative of e to the x is e to the x. And then the second derivative, well, this is just going to be 2e to the x. And now this is where our product rule is, where the derivative of the left side is 2, and then leave e to the x alone. Now leave 2x alone. Derivative of e to the x is e to the x. Now what I would do is, I don't know, factor out a 2e to the x, which I could have done earlier, I just didn't. So what do we have? 2e to the x plus 2e to the x would be 4e to the x, so I'd be left with 2 plus, because I factor out a 2, and then I'd just be left with the x, wouldn't I? And the second derivative needs to be where it equals 0. Well, here's the thing, is this piece, e to the x, is always positive. So it'll never equal 0. But x equals negative 2 would be that. Okay, negative 2 would give us a value of 0. We can make a sign chart. At -2, it's going to equal 0 there. And to the left, like -3, 2 plus -3 would give us a negative value. If we plugged a value to the right, it'd be positive. And that's pretty clear. So this would be concave down for your second derivative. Kind of explained it right there. Negative infinity to -2. Your reason is the second derivative is negative. I hope it's all named f, because I keep, yep, they're all named f. Right there. And then right here would be concave up from -2 to infinity. And the reason is because the second derivative is positive. And you can verify these results with the graphing calculator. So moving on to the next one, notice that in this case, they actually give you the first derivative. So if all we care about is the second derivative, you know, they might give away some things for you. Well, this is going to be your quotient rule. The derivative of the top is 0, leave the bottom alone. Then minus derivative of the bottom is 2x, leave the top alone, all over the denominator squared. Well, this 0 times anything is just going to be 0, so there's no reason of having that. Now, here's the thing, is where we change concavity could also be where the denominator, so the numerator could equal 0, that's when it equals 0, that's at x equals 0, but also where the denominator equals 0, because this would be where the derivative does not exist, but it can change concavity there. So I would have x squared minus 3 set equal to 0. Oh, that was supposed to say 0 up there. And, well, that would be a plus or minus root 3. Now, as far as our answer goes, we do have several things going on. Like we have this negative root 3. We have 0. We have positive root 3 as far as our sign analysis goes. But instead of doing like a full sign analysis, I'm just going to keep it as simple as possible. Because as I'm looking at in the like values that are smaller than -3, like -4, well, if I put it into the numerator, we have a negative times a negative. So what would end up happening in the numerator is we're getting a positive. And then in the denominator, it doesn't actually matter whether we square something and subtract 3 and then square it again. What I'm looking at here is we are always going to be positive in the denominator. The only thing is we can't have x equal the square root of 3. Because if we do, then we'd be dividing by 0, and that would be a domain error. So really, the only thing that matters is when we have a negative times a negative in the numerator, we're going to get a a negative times a negative will give us a positive. So without confusing you too much with the sign analysis, what should happen is at negative root 3 is undefined, at positive root 3 is undefined. And if we consider at 0, what will end up happening is we need to have a negative times a negative somehow. What I would probably do for my sign analysis, I know this does not follow the things I typically have, is because of this negative sign, I switch that 0. And then for any value for negative root 3, it actually doesn't matter because the way I'm thinking of it is values to the left of 0, these things will always be positive once we square in the denominator. I know this doesn't really heed what I typically say about these things, but what I would mention then is that this graph is concave up for negative infinity to negative root 3. It's undefined at negative root 3. And then from negative root 3 to 0 because the second derivative is positive there. And then concave down from 0 to root 3, union root 3 to infinity. All right, so I'm trying to give you the sign chart correctly done without confusing you too much. Because if I were to switch over to the answer key, the author of this would just give you specific values like -2. Well, if you put in specific values, yes, it works for -2, but does it work for -3, -4, things like that? And you want to look closely at the graph, because a negative times a negative would give you a positive in the numerator, and the denominator is always positive because you square that number, and it can't equal 0. So you do want to mention that as well as you move forward. Just real quick, I'm going to give you my explanation of the second derivative test. By the way, you are allowed to explain things with the second derivative test, but it's never a requirement of Calc 1 or Calc AB. So I'm going to explain it to you, and you don't have to do it this way. So let's say you work through a problem, and let me change that x to be a c instead of x. F prime of c gives you 0. So that tells us that c is some critical number. The second derivative test is then saying, okay, well, if I do the second derivative and I plug in that critical number c, well, we have 3 situations. We can either have a positive number, we could have a negative number, or we could get the second derivative plugging in c to equal 0. So let me try and give you a picture real quick of what's happening. Well, remember, if c is a critical number, it could be a min or a max. So let's say that we found the c is a critical number and it's concave up. Remember, if it's positive, it's concave up. So what that means is it needs to be at the bottom of a curve. So that tells us c is a min. And let's flip the other way. If c is a critical number and it's concave down, then it's going to be at the top of the curve. So c is a relative max. Now here's the thing, is sometimes we plug in c into the second derivative and we get the second derivative also equals 0. This one tells us nothing. It could be a min, it could be a max, or I don't know what. So let me just share the answer key with you, because he writes it out in words. It might make a little bit more sense. But this is how I remember, is thinking about, well, what kind of concavity does it have? Is it concave up? Well, if it's concave up, it must be a relative min. If it's concave down, it must be a relative max. So continuing where we left off, this is just how the words are written out, what you would probably find in a math textbook. So go ahead and pause the video, write down what you feel is necessary, and then I think I need to make a third video to explain everything else.